whether I am audible or not. Am I
Yes,
audible?
sir. Yes, sir. You are
Okay.
clearly audible. Yes.
So good afternoon to all. So today I'm going to say a few things about the data science. So I'm just going to share my slides. Is the slide is visible to you?
Yes, not for now. Need to wait for a second, I think so.
Is it visible?
Yes, yes, sir. Yes, sir. Now it's visible. Yes.
Okay. Is it in full screen mode?
Oh, no, sir. It's not in full screen mode.
Okay, let me.
Yes.
Now?
Yes, yes. Perfect.
Okay. Okay. So today I'm going to say a few things about the data science, as this workshop is on data science only. So, I hope that all of you know the value of data in today's world. Everywhere we are seeing that the data is around with us. So there are some quote here that you can see in this slide. But the data is really important for all of us who are dealing with like data management, maybe business. And this is the kind of obvious things in today's world. It is not a new thing. It started early on with the big data. Apart and the data driven, and then the data science evolved from the big data. So you will see that a lot of discussions of this type of topic in daily media. The two terms, big data and data science, etc., are all intermixed. They are interlinked. It is not hard to find a lot of comics. So we are now even into the deliberated world. So when you have deliberated on data science, then you know that you probably made it. So now, here you know that according to the Google Trends, so you know that according to the Google Trends, you can find out the interest of data science in Google Trend. We look the term big data, then data science, then data analytics, and looked at the how those phrases are trending. So sum them up, and then top lines here, the top lines here shows the sum, and it clearly shows the significance of our interest. So a few years ago, there was this word cloud that was made, and if you look at it, then you will see the confusions here. You know, even in the definitions, we have these confusions of data mining, then data science, then machine learning, then computer vision, and so on. So here, what is our objective today? To know some definitions and at least come to a working definitions that we use in our daily life. Then we look at some data science applications. You might be surprised why the data science applications are discussed at the beginning, because here the data science is all about the applications only. So I wanted to give you some examples of what can happen in data science in most of the important parts, mostly of time that will spend around the next three areas is so along with the data science applications, we will also talk about the data science ecosystems, And then what is the data science life cycle? Then what is an architecture for the data science system? How can we architect these things? Will end at the end, we'll see who owns the data science. And because this is really a significant amount of discussions is required. So I'm not going to read all these things here, but there are multiple definitions of data science, both in academia community. Indeed, there is a sampling of those definitions, although the definitions are somewhat different. So they have word phrases. So I think Wikipedia definitions starts out well, but then it is basically ends by saying similar to data mining. Similar, it is very ill defined, of course, but it's trying to even loosely equate data science with data mining. So, but the things that jump out on these definitions, in that we are talking about the data driven, then decision making. We are talking about looking for and finding patterns in the data. We are trying to, the objective is to get some insight from the data. And from this pattern, use it for some applications. The definitions also include that things is a process. So it is not a one shot, you do something, so it happens, there is a process involved. So the definition which I like the most is this. So it is a data-driven approach to problem solving by analyzing and exploring large volumes of processing multimodal data, extracting from it knowledge and insight that is used for better decisions making. Then the following sentence in the definition emphasize the process perspective that will come to the fore quite a bit. So it is the process of that starts from collecting data, then preparing data, then managing the data, analyzing the data, and exploring the data, the results, and last, the results. So that's basically the working definitions of the data science. In the context, we will see the data science as an unifier. Now here there are two perspectives. We can see the diagram from two directions. One is from inside to outside, another is from outside to inside. So it is a unifier. You can look at this Venn diagram. Now, if we see inside out, then you are basically saying that data science is unifying all of these disciplines. And if you look at outside, then it is the fact that these disciplines have an impact on data science. So there is, of course, the questions that comes out when you talk about what is the data science. When you want to define it, the questions that comes out is who is a data scientist? Who makes a data scientist? So I'm going to leave that until the end. So let me talk about what we view as a data science. And then we'll discuss about the data science at the end. So that differs from some of the things that you might have read or watched on YouTube, because you know that there are lots of material are there on YouTube on this topic. So there are two myths that we want to tackle first. One is that data science is big data. So it is the same thing as big data. So in popular culture, in popular print, or in popular media, they said that their equivalence or the difference is very, very limited. But you know that they are really not the same thing. Big data is like a raw material. So it has a lot of potentials, but you have to do something with that raw material or with the big data, and doing something with the raw material is the processing it. So which is a part of your data science. So where you gain better understanding of what we call the data. What the data is modeling, and in that context, the applications are really important. So if you do not have applications, you have big data, then the big data processing, but applications derive what the data, what you are looking for from the data. So I think this myth, at least for us, now we need to clean this up. So it means that from this, we are getting that the big data and the data science, they are not same. So big data means the raw material, and the data science means when you are processing on this raw material to get some insight out of the big data, which are actually known as the data science. So the second thing is this discussion, which happens almost in every computer science unit, which is, well, is not the data science, a subset of ML, a pro, and which is a subset of AI. And some claim that the modern AI is all about his old ML, machine learning. So there is this notion that data science is really nothing more than machine learning. And if you really listen to a lot of conversation, you'll see that when they talk about the data scientist, they are talking about the machine learning people and the machine engine people who engineer machine learning tasks. So I think this is fundamentally wrong. I think there is an overlap between the data science and AI to the extent that we use machine learning and data mining together. So as a part of the analytics, but it is not even comprehensively all of the analytics. So they are related. They do have an overlap, but they are not the same thing. So data science, many other concerns are that have nothing to do with the AI. So AI has a lot of concerns that go way beyond the data science. So their data science worries about. So with that, let me talk a few applications to give you a sense that the questions typically comes up of what makes a good data science. What are the good data science applications? So with the so if we answer the questions, where we can apply the data science, then the answer to that is actually straightforward. If a domain is using very large data set or generally large data set, that it's a good candidate for being a data science applications. Example are many. So we could list a couple of examples here. So one is, of course, the sustainability. So you know that in today's world, there is probably one of the most data science applications of today's world is the sustainability. So given the challenges we face around global environment problems, it covers a lot of ground from climate variability, change to ecology, to food, energy, and water concern. The challenges are great, but the people who work in the area also know that there is a tremendous amount of data that comes in various form of Earth observations data. So remote sensing again is another applications. Then citizens science data, and there are many such applications are there which are actually related to the sustainability. The hope is that all of this data can be leveraged to better understand where we are, when and what the impact of the data, what we and our actions are, the answers of what the type of questions, and decide where we go. Another applications here is biological and biomedical. You know that there is an exploration of data here in this field. A lot of interesting problems can be addressed by data only. So you all know that there is now quite a bit of research on what is called mathematical and computational medicine, which leads to more personalized medicine and so on. So these are given example of data. A more everyday example is fraud detection. Again, it is one of the important applications of data science in today's world. So which is looking at fraud pattern in past data. So we know that we have the past data. So from the past data, our objective is to find out fraud pattern. So if we can find out the fraud pattern, then we can easily detect whether there is a fraud happens or not. So in the example that we mentioned previously, we are looking at what we call data at rest. So we collected the data. So here data is stationary. It changes, it's a time, and there is dynamicity, but fundamentally we take a snapshot and analyze it. In fraud detection, we are looking at real-time data. So what we call the streaming data. So data is coming and then the streaming rate. So we are trying to find patterns typically. So here we use windowing, and we look at the certain amount of data, see if we can detect certain activities. That's clearly our data science applications. Okay, so here we are talking about the few things. Again, we are talking about the real-time data, and real-time data, we know that it is known as the streaming data. So it is really difficult for us actually to analyze the real-time data or the streaming data. So what we can do, we can consider a windowing, and then we can collect the data of a particular window, and then we can analyze. And after analyzing, if we can find out some activities, some patterns which actually says about the frauds happens, then actually we can find out the fraud detections. Then there is another important application is the recommender systems. Nowadays, you know that it has a lot of use here in real world applications. Again, this is really an important one. You know that a Netflix recommender system is valued at $1 billion in a year. Amazon is again another organizations which has used the recommender system a lot, and they're claiming that to derive 20 to 35% lift in their sales with the help of this recommender system. So commercially, these are important. Again, we are looking at both the data at rest and data in action, which is transactional data. So customers buying stuff, and customer liking stuff, and customer touching even item web page. So these are some of these applications, but there are many others. Now let us get to the core of the topics that we want to talk about, which is the ecosystem. So this is really where we take that unifying view, which is probably way too inclusive, and bring it down to basically say, this is our car. So this is, if we are going to have a discipline, then this ecosystem will be the core of this discipline. So there are basically 4 building blocks of data science, which are actually known as this data engineering, data analytics, data protection, and data ethics. So all of these 4 building blocks are equally important. So we cannot ignore any of them. All are equally important. In most of our daily conversation, when people talk about a data scientist, they are really talking about the data analyst. That's the mental model that most people have. But all of these 4 fields have significant impact on the field of data science. So we cannot ignore any of them. So these 4 building blocks are surrounded by applications. So the applications both impact what these core technologies should be providing. Hopefully, what we do in the field of data science inform how we handle these applications. Also, all of these building blocks sit within the context of a social and policy context. So none of the data science project that we know of occur in a vacuum. So they are very much influenced by the social context in which they take place. The certain thing that we might be able to do in India, we cannot do in the other part of the world. So the social and policy context really influence what we can do in data science. So this is the ecosystem. This is where we said we need to worry about all the 4 building blocks. So we'll take each of these and say a little bit and to expand them. So the data engineering is the first one. It is everything that we do in data management, but not everything we do in data management. It is the things that we do relevant to these definitions of data science. So that consists of 2 things. One is the big data management, then data enrichment, then data integration, and then data storage, and querying up a very large volume of data, maybe ETL and or ETL processes. So if we are doing data warehousing, maybe we are not doing any of this, but data lakes is the integration mechanism. What are the underlying platform that we use? So we'll talk about this platform, both hardware and software platform, but in terms of the managing the data. The second is data preparations, which is the data acquisitions, gathering, then data cleaning, then data provenance, then data linkage, and so on. So we put these 2 as 2 points in data engineering, but we do not mean to suggest that these are totally decoupled from each other. So as you will see, when you start talking about the processes, these will get in enlightenment here. So why data engineering is a part of data science? So we think it is now not the big concern, because even this started reading publications which actually says you cannot do AI unless you do data engineering properly. So I think that's now becoming far more understood, but the fundamental reason is the very simple. So we all live with which is you garbage data, garbage result. So it's really, if you do not want to do the data engineering part right here, then you are going to be the data that you put into your great model. Okay, then the super model is going to be fairly ineffective. because you have not done the data engineering before feeding the data into your model. So the results that we'll get are going to be fairly unreliable. So data engineering really makes sure that the data garbage, that this data garbage is not occurred here in your data. So before doing anything, so we need to actually play with the data engineering part. So here we need to ensure that the data that we have, this is clean enough, so that the predictions that we'll get actually will be less erroneous. Then only we can rely on the data result or the applications. So just one slide on what we mean by big data. So there is no definitions, but there was a NSF call for proposal some years ago. So big data was that entire working group has not transformed into a data science group. So you have to really dig to find the solicitations that they are on the web, but it's basically the definitions is a better farming of what we call understand the big data to be. But fundamentally, we use the 4 V's typically to identify the big data, but the volume, the variety, the velocity, which is the streaming nature of some of the data, and then at last the veracity, which is actually how well you can believe is an issue. So the leftmost figure at the number here at the upper right corner of the figure, that's the 175 zettabyte is what is expected in the next few years. So that's a very high number, even for database also. So it is a challenging volume to deal with, but the management of this data is really an important issue. The data preparation is typically seen as a workflow, which starts with data acquisitions. So we need to find the data sources that are appropriate for the problem. So we select a certain set of those data for the problem. So we typically integrate, but that integrations we should put into quote, because here it could mean different things. So as we'll discuss a little bit for this case here in data science, and then we have to deal with the data quality problem. So that's the data preparations pipeline at the end of you get. So this hopefully minimally the junk in data is minimized and you can use it for proper analysis. Sorry. So there are multiple ways of data integration. The classical way is this use, since you are getting the data from big data source and the data is multimodal. So what do you mean by the multimodal here? By multimodal, what we mean is that it is a structured data. You know, unstructured data like graphs, tweets, social media stuffs, text, a lot of text and so on. So you are not going to have a single store typically. So what you do is that you might have a federated data store that we have. So this multimodality, that's getting that transactional data, but more importantly, traditionally, what we do is that we take this data and put it through an ETL process, which is extract, transform, load. So you extract the data from these sources, transform it to the schema of the target, and then load it to the data warehouse. So the modern twist is that the modern twist to that is ETL, which is actually extract, load, and then transform. So you basically do the transform after you are loading. And this is the data warehouse approach. Then you migrate the historical data from your transactional store to this data warehouse. Then both of them feed into the data stream tasks that we'll talk about. So there is a traditionally what happens, but more recently that there is a notion of data lakes. So here you can see here, and the difference is that the data warehouse we call a schema on the right. So you are putting data into the data warehouse. Data make sure that the data fits the schema. So data lakes are called the schema and read, which is that you do not care. So you just more or less dump the data into this integrated store, and you worry about the schema when you are reading or when you are doing it. So it is in this arrow here, there goes to the downstream tasks that you have to actually give a shape to the data so that it can be used. So there are these two alternatives. So the data integrates the data lakes are our definitions is given here, which is massive collection of data as well as data warehouse, like the two. But there is a federation here, so it's not physically single store, it might be distributed. So they might have different formats, and some might have the metadata also. We call schema, so some may not have the metadata also. So they may change autonomously over time. So most of the literature, when you read, you will see that the data lake is a single store, but it does not have to be a single stock. So the difference between this are from our data engineering perspective are what you would expect. The data warehouse is a simple to architect because you have a well-defined schema for it. So it is a single star. It is a central line. We do centralize analytics on it here. So the analytics algorithm do not have to worry about it. But there is now a growing concern that this creates privacy concern about the data being centralized. On the other hand, we deal with distributed data, sometimes autonomous, but we can do that is really popular now, which is federated or distributed analytics, or this in machine learning world. So this has become quite a popular topic in today's context, in today's study. Those seem to reduce the privacy concern. So all of this make the data engineering part of data science. So whenever you integrate, you have data quality issue, because you know that they are in different sources. So when you need to integrate them in order to do the analysis further, then definitely there will be an issue. The literature is full of discussion of how big a portion of the business world worries about the quality of that they deal with. So there are all kind of again comics that go around that talk about what these data quality issues are. So we mostly talk about the data cleaning here, but the definitions which is the DAMA in the Data Management Association in UK, they have defined these 6 definitions, 6 dimensions. Originally, it has the 6, then it grew to 550, as these things typically do when you get communities involved here. Then they distilled it to 15, but this 6 probably give a good idea of what the dimensions of the data quality are. An important part of this data quality, and even going into the private sequence that we'll talk about later on this data provenance, where the data is coming from business purposes, which is play a significant role here. Then the second part of the data science ecosystem is the data analytics, which is really the use of the statistical and machine learning techniques to draw insight from the data under the study. So you make predictions about the behavior of the system under the study. We will again come back at the very end, but just as a teaser, this is the discussions between the statistician and the computer scientist, especially the data mining or the machine learning people who really doing the data analytics properly on big data. So this definition, this distinction is not the important, or is probably the disappearing. So there is a paper by 3 researchers who are not really the computer scientists. They are actually the biologists. They argue that the statisticians typically deal with the smaller data set. They try to build a model. They deal with a limited number of attributes. So if your number of the attribute really grow large and you are trying to make big data predictions, then you are in the machine learning world. So take it for whatever it is worth. But you know that the type of data analytics are typically the diagram on the right shows the increasing complexity along the x-axis and the value presented value here along the y-axis. So the close to the left corner is the descriptive, which is really looking at past data and trying to decide what is happening. What does the data tell us about what is happening here? This is exploratory analysis, is a part of this as well. So you may not have direct questions or clearly from the questions, but we are exploring the data, and then we are actually refining your questions as you go along. So the next one is actually the diagnostic. So again, you are looking, and it is backward looking. So it's looking at the past data, but not only are you trying to say what is happening here. So we are trying to detect why it is happening. So we are trying to diagnose the reason for whatever is happening here in this system. So what the data suggests about the reason, then we move into the predictive, is not a retrospective. So predictive is looking forward, and it typically uses the machine learning, data mining, and predictive modeling techniques to determine what is likely to happen. How are the decisions going to be affected by what is likely to be happen? Finally, perspective, which is again forward looking, but it builds on predictive to basically say this is what we should do. The argument is that it gets more complex as you move from the descriptive to perspective, but the value of the analysis also increases as you go in these directions. So here, all of these are valid within the context of data science only. So when you look at the data analysis, the text and methods, they are typically 6 that we can identify. But clustering is one, which is finding groups and structures. So that are actually similar in some definitions of similarity. Then outlier detection is another one, finding anomalies and the rare items. You know that the fraud detection is a good example of outlier detections. Then We have the association rule mining, which is finding relations between variables, and market basket analysis is a good example of this, the association rule mining. Then we have the classifications, which says, or which is really generalizing and known structure to new data, so that you can take that new data and classify it in one of the groups that you are defined. Then we have the regression. So regression is a model that best fits the data that you have. Finally, summarizations, which is a more compact representation of a data set, and typically visualizations that actually shows you, it gives you a significant amount of insight of the data. So what is going on here? So if you link this, the previous slides, then that typically clustering, association rule mining, and the summarizations. Again, clustering, association rule mining, and the summarizations techniques are used for descriptive analytics, while the classification, regression, and outlier detections are suitable for the predictive analysis. So within this context, we should talk about the analytics architecture now. So if you are really integrating the data, you have an integrated data store, then you are typically doing a batch analysis on this. So you do analytics, whatever analytics problem or the formulations you have on this data. So it is a patched, and if the data changes, you can come back and it incrementally. But it is basically a process. There is the new area, which is federated analysis, where if the data is not integrated, but it is not a federated form, then you can push the analysis into the sources where the data resides and do the analysis there. The common perception now is that this has advantage in terms of data privacy. Finally, there is a real-time analytics. So if you have a streaming data, so that's coming into your system, then you do not really have time to create these data stores. So you can have at the best real-time store, which is actually really a very lightweight main memory type of data store. So you do a transaction analysis on this one real-time analysis to provide the real-time analysis result. That's the second part of your ecosystem. Now, the third part of the ecosystem is the data protections. Now, the data protections becomes a really big issue nowadays. So it is more general term for what is called the security and privacy. So it becomes really a big issue in data science simply because of a big data problem that you are collecting, possibly integrating, possibly federating. So all of this data, and these are far more surface for attack in this kind of environment. So that you really need to worry about. So when you look at the dimensions of the data protections, there is of course the privacy and the security dimensions. The privacy deals with the proper handling and processing, storage, and usage of informations. On the other hand, security deals with the protecting the informations from any unauthorized access, malicious attack. So this comes in various different concerns, from policies, privacy policies, to privacy enhancing technologies, the third-party management, and the data subject access request management, and so on. On the other hand, encryption is the stuff that we all deal with. In particular here, you might have to be dealing with encrypted data, or at least one posing encrypted queries over encrypted or unencrypted data. So homomorphic mark encryption is quite popular here. So these are trusted execution environments that are now appearing in hardware for being able to do it, and so on. So the title is data protection. We talk about the data privacy. We talk about the data security, but the data nature, but the nature of this change a little bit when you go from classical or traditional security privacy concern to data security and privacy concern in data science. So what comes to the fore are the bigger privacy concern. Also, the veracity of it. Veracity, you know that veracity means the uncertainty in data, which again increases the complexity of the overall system. And there are a lot of issues here, you know, that how we can actually deal with this uncertainties of the veracities of the big data. Again, it is another discipline actually. So now, how do you deal with this misinformations and so on? So those become to be the four. When you look at the type of these threats, the threat surface again, as you said, quite broad. So deal with the data breaches, surveillance, misinformations, and infrastructure attacks. So really, the threats are across the entire spectrum because it is on the entire spectrum. So people are actually started saying, well, so we are really do not want to talk about the data protections. We are moving into cybersecurity, which is that the entire system at all level need to be protected. So you need to be protected your platform, you need to be protected your network, you need to be protected your software, you need to be protected your data. So all of this play into the data science. So there is a significant amount of issues here. So this Cloud Secure Alliance or CSA, they made recommendations on the type of things that we should be worrying about in terms of the data protections in data science applications or the big data applications. So we have listed them here. So they go from the infrastructure security to data privacy, the data integrity, the integrity of the data management issues, both in the data transforms log and the data provenance appear quite a bit here, and reactive security, which is basically coming back and being able to do audit. So the fourth and the final building block of the data science is the data ethics. So this is a topic that is very rich. It is studied in different areas. So this is actually the definitions from philosophy. It says it is the branch of ethics that studies and evaluates the moral problems related to data algorithms and corresponding policies. So if you, what the definitions gives you are 3 dimensions of the problem that you need to consider: ethics of data, ethics of algorithm, and the ethics of practices. So what we have done mostly here in the space, in the more in the STEM world, is to worry about bias. So that's a lot of work that is on unbiased. The bias is a kind of systematically distortion of the statistical result. That's what happens. Psychologists indicate that their bias is actually inherent in human decisions making for 3 reasons. One is that humans want accuracy, which is the correct decisions making. So we want to make the decisions fast. We want efficiency. When we are actually considering a decisions, then space of alternatives is too large. So we want to actually narrow that the space of alternative. So those 3 are our actually main reason why bias occurs. So the type of bias that like psychologists identify in humans are fall into these four categories. So we have highlighted in red the ones that typically come up in the data science applications. Overconfidence in our ability, which is actually action oriented bias. So we know what we are actually doing, anchoring effect. Mentally we are at a space, we are at a particular place where we are at effect. So what alternatives we are willing to consider? Confirmation bias is really quite a popular one. So it is, the confirmation bias is one where we say we have a hypothesis, we are going to focus on the data that confirm our hypothesis enough. We'll see the data equally tells me that what we was claiming is right or wrong. Then the social bias, which is actually appear mostly in this context of data science as a group things, or the going alongside said that we do not want to actually rock the board and go with it. So when we look at this in device in data science, there is a bias in data. For example, machine learning deployment, this is the bias in the training data. So it could be introduced by a historical or representational bias. So historically, more of them show up in the data bias might also be introduced due to underrepresentations. So you know that we all know the probably about the Google doing the initial filtering of applicant CVs that they had to scrap because they were using a system that relied on the data. And you know that here women were not represented sufficiently in the data, that become an issue. So the other issue is the bias is algorithms or model. So the certain individuals attribute are commonly labeled or protected attribute because they cannot be the source of social bias, such as race, religion, etc. So one needs to be really careful about that. So there are stories that is quoted here, which is actually, they basically indicate that the bias in the inclusions or omissions of these certain features in the model itself or in the algorithm lead to bias. But we talked about the bias, but bias is not the only part of the ethics. Bias is actually highlighted because that's what we spend a lot of our time. So most of our work has been actually on gender bias. We talk about marginally communities. There is a significant bias against the First Nations, etc. in a lot of our data collections. So those need to be brought and considered carefully as well. The unmeasurable outcomes, the typical example that's given here is that when we are admitting our students here for suppose the bachelor courses, we try to determine who should make a good student. And since we cannot know, we use, that the JEE main score or the advanced score as a proxy for success. And this score are known to be really bad determinant here, because bad determinant of a student success. So the number of places, including us, giving up this GRE score. Sorry, this main or advanced score, but that is another issue. So when you broaden the scope of to more ethics of data, then you have a lot of these other issues that you need to be deal with. The ownership of the data. Who has the ownership of the data? You will notice that some of this crossover to privacy concerns, the transparency with the data, we need to know, and we need to consent the privacy of the identifiable informations and the intentions for what processes are you collecting the data. Then you are not going to use it for any other purpose other than that those are all ethical concerns on data. So we cannot say that we do a very good job in our training of these students on the ethics issue too well. So, you know, the Berkeley, USA, there is a big data scientist group actually. They have released a checklist here, and the checklist is shared here. So it is a pretty good checklist here. So this is the card actually, and these are the core that we need to deal with in data science here. Now let's talk about the data science life cycle here. So, you know, the many of us probably know that this data life cycle, the data life cycle for some of us go back a couple of decades, but this is from a paper that's fairly recent. So we picked that the one it is summarized in it fairly nice. So data has a little data has a life cycle. It starts when we acquire the data. So the life cycle starts from acquiring the data. So now we clean the data, we use do something with the data, or reuse it multiple times. We publish, where we share the data, then preserve the data for some times, then destroy it. So this is typically called the data life cycle. So there have been a number of variations of this that have appeared in different contexts or over year. So some actually predate so this particular figure, but nevertheless it is the variations on the strain, the way that we look at the problems with this type of dealing with a life cycle is that it is linear. It gives the impressions that you start from here, you follow these steps, and then you are at the end. But we think many of us know that this is not the life cycle of data. We keep going around in a loop and repeating it. So there is an alternative model, a TIPS data mining model that the data mining talks have developed about 20 years ago. That is still quite popular according to the recent study. And this is called the PPDAC model, which is really a statistical model. So it is the same thing. The PPDAC is the name or the name of the phrases. So it goes in a cycle. It starts with a research questions, which is really the problem definitions. Then everything starts with problem definitions. So if you are for an applications, then there is where you define applications requirement. Then you do the data preparations, which is collecting the data. Then the data set, the selection of the data. Then ingest the data, quality issues. So data provenance issue. Then you store the data for integrated, etc. And then you do the analysis. Then you do the deployment, which is actually the disseminations of the result. Then you do the deployment. This last bit, going back to the research questions, is where do you monitor? You repeat this process multiple times. So all of this life cycle is surrounded by the data security and privacy. So the data ethics and social policies issues, that's they all influence it. So this is more or less the process, but we see the process more as a cycle, and this data security and privacy. So the data ethics policy issues have overlaps with each other of these boxes. So we'll show some of the questions that come up when you take the data security with each of these boxes. So what happens there, and in each of these boxes, that when you consider what kind of security and privacy concerns you have, the final things that will tell and show this process is important. The final thing that we'll say here is that we all that there is a fault line and the font in this, so this type of circular models, as well as in this sense that it gives the appearance that when you deploy, you monitor and you come back, you refine. The research questions, you are back to where you started. So it is, of course, not true. So there is a kind of dialectic process here, and that you come to a better understanding. You are hopefully improving your understanding and go forward. The more important issue is although we have these boxes of the processes, and each of these have their own problems. So what happens at the interface is probably more important than what happens in the boxes, or at least just equally important. So we should never lose sight of these interactions between these. So now let us talk about the architecture briefly here. So we'll summarize this beginning part, and this is from NIST, National Institute of Standards and Technology in USA. So this is a fairly nice model. The important part of this model is that it separates the data frame by big data framework providers from the applications provider. The application provider is really the process, and so this is the life cycle. The life cycle management from ingesting the data to preparing analytics, visualizations, and providing access to the data concerns. The big data framework providers provides the underlying infrastructure for the. So these are actually organized along two dimensions. One is the management fabric. How do you manage this entire enterprise? In the stack here, the other one is the security privacy fabric. So this architecture has made an impact. So here is one that we are showing where somebody modified it. Some researcher modified it for really data science applications in the national security domain. So it does have an impact, and this is not the only architecture, but there are some. So this is a good reference architecture, which actually tells us what type of things we should worry about. But what is a really concrete software stack? So if we want to build a system, what we do? What we need to do actually? So this is what we come up with these systems because of this big data context. So they are going to be a scale out systems. Because they are going to be a scale out systems, so we have a actually computing infrastructure, which is a scalar computing infrastructure. Then we have a system platform, which is really distributed data storage. However, manage this, then we have a processing platform, which is both dealing with the data in motion streaming data and data at rest, with perhaps some common interface. Then an application platform, which is our actually the workflow, because this is a scale out system, we need resource management, the privacy security technologies across all over these places. So this seems to us to be a reasonable stuff. So there is, if we are doing the cloud, if this is mapped to the cloud, then there is actually standard mapping. We think the system platform, computing infrastructure together is a platform as a service. Then we can go up the stack, and there is a lot of work that is done in individual piece of this. So there are a lot of systems that people have built. So they typically, where the people build these stacks now is by gluing this together. So there is no monolithic architecture that properly might be there. So might not be ever a monolithic architecture like the one that we are used to. So there is another view of this architecture that some people have exposed, which is actually really says well. So we have two types of data, the data in motion and data addresses. So why we do not, we track what we do to those two different types of data. This shows that there is this batch processing side, there is the streaming data processing with real-time analytics and batch analytics. Sometimes you do combined analytics. So that's another view. So now let us end the quickly with a discussion of who owns the data science. You know that the one on the right is the statistician views of computer scientist. If you look, we have read a bit, statisticians have been arranging and to certain extent the rightfully that they are been doing the data science all along. But the what we have been doing all along is the data analytics. So they are only dealing with the dealing with one component of it. So if they are not dealing with the everything, so the one thing that you might have seen. So in this view, which is actually very well known, the Conway diagram. So this is very popular among the statisticians. It is highly cited here. The Conway diagram, if you look at the this Conway diagram, you will actually see that there is no role for computer scientist or for computer science. The Conway actually in the accompanying back forks, he says this does not require the background in computer science. So all you need in data hacking, so you need a lot of statistics on math, where they meet, put together with the substantive expertise in this domain knowledge in data science. And that's basically a popular diagram. So when you have that diagram, there is a counter diagram. Actually, this is very interesting. So if you search for it, it is called the Battle of Venn diagram. It is a KD nuggets. There are actually zillions of these Venn diagrams that people have drawn. So it makes for a fun reading. But now the Duellman wrote this, and he basically says, well, you know that the machine learning, all computer scientists, so it is nothing new. So you need a little bit of statistics and maths. So math is actually important, statistics is important, but it is really the interactions of computer science and the domain of sciences. The data science is all about this. Even machine learning is only the part of the data science. That's his view. So AI encompasses machine learning, and machine learning encompasses the data science. So it is AI, we are done. So let's leave that aside, these two conflicting views. So who are the stakeholders here? So there are actually three types, there are three stakeholders that we can identify. So these are, there is a group of core technologies people who actually technology development. So there is a whole group of applications, researchers who actually do not do technology development, but they are actually either in STEM or in social science or in humanities. So digital humanities is a big thing who are involved in data science applications in some domain. So they want to use the technology that the first group develops. Then there is a third group which is actually worried about the ethics, the social impact of data science, how this plays out in the society, what the policy dimensions are. So those are actually the third stakeholder. So if we have to use the Venn diagram here, it is actually worthwhile to be inclusive while establishing the car. So who is the data scientist? So given the code that we describe, what are the core competencies here? Here, one should be an expert in ethics, data science, data engineering, or data analytics. So whatever you need to be, you can be in data science, but you need to be in one of those courses. So you need to be have working knowledge of the others, the three pillars. So you need to understand what the data, what the the data protections issues are, and what are the data ethics issues are, and so on. So you have knowledge of multiple applications domain, but at least one, and you need to be able to work in a team, because the data science is never done alone. So it is always a team effort. So that's what we consider to be the data scientist, at least from the same perspective. So with this, actually, I'm concluding the today's the lecture. Now, if you have actually any issue, please let me know. So here, I want to mention one thing. The slides that I have shown here actually is taken from Professor Udshu here. He is in actually the University of Waterloo, and he is working in this domain since last 50 years. Actually, he's a senior researcher. So I must acknowledge him. So whatever he has discussed, I have tried to deliver the same thing here in front of you.
So yes, sir, we are having some question in the chat so that I can read it one by one. So one of the participant has asked about what is TEE full form.
T double T.
TEE.
T double E. Can you tell me the slide numbers actually?
Yes, Narayanji, could you please post the slide from which
Yes,
slide
I,
you
I,
are
I can share the link here to the participant actually, or I'll share the link to you actually, and you just share with the participant.
Sure, sir. That we will do. Okay, so
Is there any?
yeah, yes, sir. One question is If the data is too large, how the data science deal with it?
How the data science?
Deal with it.
Yes, as I have told you that we have said here two things. One is the big data actually. Big data means the raw material actually. And you know that in most of the data science applications actually, we want the big data actually. Otherwise, the decisions that we will take will not be actually sufficient. Now, there are few things. So here we have mentioned in the data science architecture here. You know that the federated means it is some kind of the centralized data actually. But nowadays, you know that the data they are in distributed systems here. So we need to actually take the data from these distributed systems and put it in a platform, and then they do the analytics in order to take some actually the decisions or the predictions which are actually required for organizations, for any organizations here. So if the data size is now, you know that we do have actually the plenty of resources where we can keep the data easily actually. So this is not an issue actually. But the main thing is for data science applications actually we need the big data. So big data is the raw material for the data science. And so data science means here the processing that we are doing on the big data is actually the data science. So they are not the two things. So big data means here mainly the raw material. Okay, so it is more concerned about how we can store the data here. And data science means here we are mainly dealing with how we can deal with this big data for an organizations.
Sir, next question, Mr. Anil is asking about the link of resources.
The link of
resources.
Yes. I'll share the link. I'll definitely share the link after this presentation.
Yes, and referring to TEE, the title of the slide is Dimension of Data Protection.
The dimension of data
protection.
The dimension of data protection. Okay, let me search here where the TEE is there. Is there any other questions, ma'am?
Yes, sir. There. Other question is related to DSA, PETs, and DLP.
What, ma'am?
DSA, PET, DLP.
TLT.
DLP.
DLP.
Sir, are you able to see the chat?
Okay, just
yes,
let me.
I am referring from
yes,
there.
I can. Yes. Which type of algorithm using sentiment analysis? So here actually just I have briefed the data science, what do you mean by the data science, what is the data science life architecture or the life cycle actually, okay, and data science ecosystem. So later on actually there are, you know that the course starts from today only. So you can get actually many sessions where you can see how we can use this. I mean, we have the different application algorithms, especially the machine learning algorithms. So which are actually used here in different problems like sentiment analysis. So I hope that you can just wait for a few days or maybe few classes actually. You can get the answers of these questions. Yes, here we have not actually discussed about the data protections here, as I have again told you that here this is the introduction class actually. So here you know that there are different the different algorithms are there actually, which are actually required for this data protections here. So in that actually we can use this TEEs here. So one of the fellow has already written that it is actually trusted executions environment. So it creates an environment probably here. Then PETs, so here you can see the full form. Some of the participants are actually writing. Any questions, ma'am?
Yes, one more question is there. Although one of the participants has already answered, but yes, I'm repeating that question. Can we make any model based on big data?
It is possible to make any model. Any model means what actually? Again, big data is the raw material. Okay, you can say the data actually. The size is huge. Okay, and now what we need to do in data science, we need to write some algorithms actually to apply on this big data in order to take some insight, or in order to take some patterns out of it, which actually help us to take to take some decisions or the predictions.
Yes. So we are done with the questions. Okay. Yes, we are done with the question. So thank you so much, sir, for taking out the time and sharing your knowledge on the data science. Thank you so much.
Thank you, thank you, thank you, thank you, thank you to all the participants.
Thank you.